Hi, in this lecture, we're going to talk about methods for learning Ising models and Gaussian graphical models from data.
Suppose you have access to data consisting of ratings, like or dislike, for 50 YouTube videos from everyone at the university.
Okay, and let's assume for simplicity that everyone has rated each of these videos. So we have binary vectors, where each vector contains the ratings of each person for a particular video. We'll assume that everyone has rated all 50 movies.
Because the data is binary and people are influenced by the people they interact with, it makes sense to model this as arising from an Ising model.
Wait, but what graph should we use to describe this model?
That's exactly the question. We need to learn the graph describing who interacts with whom.
Ah, I see. And we then also need to learn weights for the edges corresponding to strength of interactions.
That's right, but it turns out that it is often possible to first learn the graph structure, and then it is relatively easy to determine the appropriate edge weights.
Perfect. So we have all this data, with each person corresponding to a node in a graph, and we need to figure out where to put the edges. Let's add edges between people whose ratings are very similar.
Well, this is where things get subtle. Just because two people's ratings are very correlated, this does not necessarily mean that they directly interact. It could be the case that they simply have many friends in common. More generally, effects can propagate through the network, so people who are far apart can still be highly correlated.
So what can we do? It seems quite difficult to find the actual structure of interactions.
Well, we know that the graphical model satisfies the local Markov property. What this means is that your likes and dislikes are conditionally independent from all the other people's ratings given your friends' ratings.
Ah, so if we want to test whether a particular set of people includes all of your friends, we can try to test whether the rest of the nodes are conditionally independent of you given this set. Computationally, this procedure is only feasible if the size of each neighborhood is relatively small, meaning that every person does not have too many friends, since this involves searching over quite a few subsets.
But this assumption seems problematic. Some people have a lot of friends, like Justin Bieber.
Yeah, that's right. So let's think of other ways how we can determine that there is no edge between two nodes.
By the global Markov property, two nodes are conditionally independent given a set of nodes that separates them. In particular, if there is no edge between two nodes, they must be conditionally independent given all other nodes in the network.
Ah, so this gives rise to an algorithm. We start with a complete graph where everybody is connected to everybody else. Then we test for each pair of nodes whether they are conditionally independent given all the other nodes. If so, we remove the edge, otherwise we keep it.
This can be done easily for Gaussian graphical models. Specifically, one can estimate the covariance matrix from the data, then invert it. Any entry ij in the inverse covariance matrix is 0 up to noise, precisely when I and j are conditionally independent, given all the other nodes in the network. So we can use the inverse covariance matrix to estimate the underlying graph. The entries that are close to 0 can be assumed to be just noise and correspond to the lack of an edge.
Okay, this nicely shows that there is a trade-off between the number of samples and how large an edge weight has to be so that such an algorithm can detect it as an edge. If we have a lot of samples, we can differentiate between a missing edge with value 0 and a present edge with a very small weight like 0.05.
Let's make this precise. Let's take a network with p nodes. We've already discussed that it is more difficult to estimate graphs that contain people like Justin Bieber. So let's denote the highest degree of any node in the network by d. It is known that if the number of samples is at least d squared times the logarithm of the number of nodes p, then one can detect edges that have weights as small as the square root of log p over n.
Ah, that's a very nice result that holds for Gaussian graphical models.
Why can't we do something similar for Ising models?
The difficulty with Ising models is due to having binary values. If many of your friends influence you rather strongly, then whether you take value 0 or 1 will be more or less determined by them. In that case, you will be influenced very little by one additional friend with a weak edge. You can think of this as a saturation, that can occur in binary models. In Gaussian models, a weak neighbor will have a more noticeable effect, since a continuous value always has the freedom to increase.
Okay, so let's return to your original idea of trying to learn the friends of each person.
It turns out that there are methods that can do this and work well for both Ising models and Gaussian graphical models. These methods are called greedy methods because they try to make as much progress as possible with each step.
The basic idea is to try to determine the neighbors of each node without searching over all subsets. Let's imagine we're trying to determine who are your friends.
So let's keep track of a set S that we think of as possibly being my friends. We'll simply start by adding the node that contains the most information about me.
We next add the node that contains the most additional information about you, given what we've already learned from the one node in S.
I see. So we can keep going in this way, adding at each step the node having the most new information about me beyond what's already there in S. But when do we stop?
Well, once our set S contains all of your friends, then each other node is conditionally independent of you, given S. That's because of the Markov property. The reason why this works well is that each node added to S contains useful information about you. So at every step, a certain amount of progress is made.
Okay, so S may contain a bunch of nodes that are not my friends, but not too many. And by the Markov property, each of the extra nodes in S that are not actually my friends are conditionally independent of me given S. So they can be removed in a final step.
Yes, great! You can now do this for each node to figure out its neighborhood. This specifies all the edges that we want to add to the graph.
So to find my friends, we added a bunch of nodes in a greedy fashion according to information gained. And then at the end, we removed the nodes that were added incorrectly.
There are other ways to do this that often work well in practice, where you alternate removing and adding nodes. The key to these greedy methods is that progress is made at each step. Because these methods add one node at a time, they're very fast, and you can scale them to very large graphs.